Hello, I'm back. I want to continue this example and I'm going to show the computer pictures for this example one that was solved in a separate little mini lecture. Okay, so you might remember with example one where we had y prime equals ay. Here's the matrix A. Step one was computing the eigenvalues and eigenvectors. Step two was writing down the general solution. And step three was applying the initial conditions, getting the equations for C1 and C2, solving them and plugging them back in. So I want to talk a little bit about the pictures that go with this and the geometry that we have. So let's see, we're going to share the screen here. So here's our website. You might notice that there's a new, some new pictures on the website. Here are figures of vector fields and eigenvectors. Well, vector fields is something that you're learning about in Calc 3. In fact, here is the exact same matrix we've been talking about, 0, 1, 2, -1. And the eigenvalues are lambda 1 is 1, lambda 2 is -1. That's what we got before. And here are the eigenvectors. I've drawn the eigenvectors as this blue line is all the possible eigenvectors for the eigenvalue 1. Right? They can have any length you want. So I can take our vector we chose as 1, 1. The guy goes all the way from here to there, multiply it by any constant. And I get smaller, multiply by a negative constant, get down there. Okay, so the thing that's about this line that's pretty cool is that the little arrows are in the line. And that's the geometric interpretation of an eigenvector. So first, what are these arrows? At every point in the plane, or at least at this grid of points, the little vector is plotted. So if the position is a vector y, what's plotted is ay. And I made it really small so I can see it. But at least this ay is bigger than that ay. Okay. So I've multiplied all the vectors by some scale factor. But you notice that along this line, all the vectors point. The vector at that point is just a constant times the vector from the origin to that point. That's what we say, AV equals lambda V. AV equals 1V in this case. So at every point here, at the point like 0.5, 0.5, the real vector from A is also 0.5, 0.5. If I draw its tail there, it would go way out to there. And then the picture would be a mess with these long arrows everywhere. So I make it smaller, but this vector is twice as big as that vector, and that vector is twice as big as that vector. Let's think about this line. Here, everywhere along this line with eigenvalue -2, if I take the position vector y, say down here, ay is -2 times y. So the vector down here points up and past the origin. But okay, these two directions are directions where they're directions v, where AV is a scalar multiple of v. AV points in the same direction as v. AV is lambda v. Okay? And so what the differential equation says is there's this vector field in the plane, and I have a point moving around the plane whose velocity y prime is determined by the rule y prime equals ay. That's what the differential equation says. So in fact, let's solve that differential equation here with our favorite app here, our slope field and direction field app. Okay, we're going to go to system. And we have various choices. We don't have y1 and y2 as choices, so we're going to have to use y versus x. So what is dx dt is y. Dy dt is, let me look at that, 2x minus y. So here's a picture. This should look a lot like this. Hopefully, let's see. Yeah, see how those pictures kind of look the same? What's the difference? Here, they drew all the vectors with the same length. They didn't show the big vectors and the small vectors here, or the long and the short ones. That's why this is often called a direction field. It's not really a vector field, it's the direction field. It just shows you the direction of the vector, but not its magnitude. All right? So again, at every point in the plane, x, y point in the plane, there's a vector dx dt and dy dt. At every point in the plane, the velocity is given. And we don't show the velocity vector, or we show just the direction. And then we can actually put in our initial condition. If I start here at 1, 0, in these units, in these variables, x is 1, y is 0, I submit it. Here is a picture of that solution. I determine it's that one that you might still be able to see, 2/3 times e to the t, 1, 1, etc. Plus 1/3 e to the minus 2t, okay? So I can think about, and let's draw it a little bit more accurately. Instead of Euler's method, we'll use Runge-cut of 4. It moved a little bit, if you see. Now, the thing that's nice about this is that I can think about all the different initial conditions. So through every point here in the plane, there's a solution with that initial condition, starting at every point. And you see that there's some places I can start where I go straight to the origin. What's that? Like if I start at 1 minus 2, let's erase everything else. If I start at 1 minus 2, see, I go straight to the origin. That is the solution. I don't know if you can see that. That's the solution with C1 is 0 and C2 is 1. I start at 1 minus 2, and as time goes on, I just multiply that by e to the minus 2t. The scale factor decays to 0. Or I could start in the direction of 1, 1. Let's just start it, because there's an eigenvector 1, 1. That means if I start at the point 1, 1, I want 0.1 plus 0.1, and I start with there, what happens is I just multiply that short vector by a growing exponential, e to the 2t times that short vector, right? So there are two special solutions, actually 4 special solutions. There's that one, there's that one, and there's, I don't know if I can get it, no, somewhere around here, there's a solution. See, it's really kind of hard. There's a solution, if I choose it just right, that will approach the origin as t goes to infinity. It's hard with a mouse, but I can quite easily do that with my initial conditions. I clear that. The vector is 1 minus 2. So if I start at minus 1 plus 2, that corresponds to the C2 equals negative 1. If I start at that point, again, I go approaching the origin as t goes to infinity. If I start really close to that, oh, it almost goes to the origin, but then it goes zooming out. Okay, so again, these pictures are related to this vector field. Here's the vector field, right? So we look at the vector, we think of the vector field. The eigenvectors are the directions where AV and V are in the same or opposite direction. AV is just a scalar multiple of V.